Hello, AP Chemistry students. This is section 3.6 on deviation from the ideal gas law. Our learning objective here is to explain the relationship among non-ideal behaviors of gases, interparticle forces, and or volumes. So we've already talked a lot about the ideal gas law. So this is going to be kind of a short one, but I want to talk about the conditions in which the ideal gas law becomes inefficient at predicting the macroscopic properties of a gas. Just as a review, ideal gases, we consider their volumes to be negligible compared to the volume they're contained within. So like the example I gave before is that helium and xenon, 1 mole of helium and 1 mole of xenon are going to occupy the same amount of space, despite the fact that xenon is a much bigger atom. Also, that gas particles do not have any intermolecular forces or interactions between them. So something like carbon dioxide, which is nonpolar, is going to have the same macroscopic properties as something like water vapor, which is very, very polar. And under most circumstances, these assumptions are true. However, there are some circumstances in which a gas will behave non-ideally. And like I said before, that means that we won't be able to accurately predict things like pressure, volume, and temperature using the ideal gas law or any of the equations that we've talked about related to gases under these conditions. And these are usually conditions that test the limits of these two assumptions. Um, and the particular conditions that are going to be related here are lower temperature and higher pressure. And when I mean lower temperature and higher pressure, I don't mean like a set temperature or set pressure. It's going to be dependent on the substance itself. So let's talk about lower temperatures. This is particularly those that are near the condensation or boiling point of a gas. So if you're cooling down the gas to the point where it starts becoming a liquid again, or it's starting to condense into small droplets, this is a condition in which you'll see lots of non-ideal behavior. And a lot of this has to do with taking your atoms and molecules and putting them into close vicinities to each other. We talked a lot about the differences between solid, liquid, and gas in terms of the space between the particles and their movement. In a solid, they were stuck together and definitely had a lot of forces of inter and intermolecular forces kind of holding them together. And also the volumes of the particles matter a lot when you have a solid or liquid and the atoms are all in very, very close vicinity to each other. So that means that at a low temperature, once the gas is getting close to condensing, the particles are going to be close to each other again. And that's when the volumes and the intermolecular forces are going to start to matter again, because you'll start to have more of those cohesive interactions that are going to mess with the kinetic energy and the pressure of the system. So the other condition in which this happens is high pressure. And for basically the same reasons. Because if you have a gas that's at low pressure, that usually corresponds to a higher volume, the particles have a lot of space to move around and are unlikely to come in contact with each other unless they just collide off of each other. But if I decrease the volume and subsequently increase the pressure, I'm going to force all of these molecules and particles to be really, really close to each other. And then the volumes and the cohesive forces are going to start to affect it again. And like even with the helium and xenon thing, the xenon particles are going to be a lot bigger. And when they're forced into a closer proximity to each other, they're going to have a bigger impact on the volume because they're not going to be spread out anymore. And the sizes of those individual atoms are going to start to matter. You can also think about xenon and its London dispersion forces starting to matter at those sort of compact circumstances as well, because all of those electrons are going to be polarizable, and you're going to have a lot more forces acting between the particles. So these are the two main conditions in which we see non-ideal behavior, high pressure and low temperature. And remember that they're relative to the substance itself, because like what is going to be considered low temperature for something like water, which will be above 100 degrees Celsius, since the boiling point of water is 100, is going to be a lot different than something like, say, helium, which is going to have a boiling point of like 4 Kelvin or something like that. So it depends a lot on the substance itself, but high pressure and low temperature relative to that specific element or substance. And I'll see you all in 3.7.